Hello class, welcome to this video on the EOC review, part 5. So let's go ahead and continue. So it says GR 4.3, extend previous understanding of scale drawings and scale factors to determine dilations and how they affect area and surface area. All right, so number 1, two similar cylinders have a radii of 15 inches and 33 inches. What is the ratio of the surface area of the small cylinder to the surface area of the large cylinder? Okay. So first off, two cylinders are similar if the ratio of their radii are proportional to the ratio of their heights. So in this case, we would say R1 over R2 is equal to H1 over H2. That's how we know that they're similar. Okay, so this is for similar cylinders. So I'm putting this off to the side just to kind of remind you what it means to be similar is when you have the same scale factor. And when we're talking about, in the case of cylinders, you could just take the ratio of the radius or the ratio of the heights. Now, they give you R1 and they give you R2. And so what's the relationship between the ratio of the radii and the surface area? Well, I'll go ahead and show you. So the relationship between the surface area and the radius is that if you were to take the ratio of the surface areas, that is the same thing as the ratio of the radii squared. Okay? So because area is squared, right? Normally area is a squared quantity. If we were to take the ratio of the radii, we would just have to square that number, and that would give us the ratio of the surface areas. It would tell us how much bigger the surface area of one is compared to the other, or how much smaller. All right, so in this case, we have R1 is 15, and then R2 is 33, and then we're gonna square that number. But before we do that, let's go ahead and reduce the fraction inside. Divide by 5, or let's divide by 3. Top and bottom. So in that case, that's 5 over 11 squared. So we just got to do 5 squared and 11 squared. So 5 times 5 is 25. 11 times 11 is 121. And so we have our ratio is 25 to 121. Okay, so that's how you do that. If they asked for the ratio of the volumes, so this is the formula for the ratio of the surface areas or the areas, right? The ratio for the volumes is going to be V1 over V2 is going to be cubed. So it's going to be the same thing here, but cubed. So I want to keep that in mind. Also, you could also use the height for this. So you could also say that the surface areas, the ratio of them is equal to the height 1 over height 2 squared. But we're not given the heights. We're only given the radii, so we have to use the radius here. Okay, so just something to keep in mind. This is for, I'm going to put this in a bubble. This is for volume. This is for area. You want to know both of them, so just in case they ask you that. On a regulation chessboard, each of the 64 square spaces have side lengths of 2.25 inches. The scale factor from a regulation chessboard to the world's smallest handmade chessboard is 4 out of 225. What is the area of each square space on the world's smallest handmade chessboard? Okay, so first off, let's go ahead and call the area of the small chessboard area 1. Okay, so this is the small one, which I'll call area 1, and then this is the big one, which is the regulation one, which is I'll call that A2, okay, for the area. Now let's go, we need to get A2, so let's go ahead and do that first. So to get the area of the regulation chessboard, you want to know that there's 64 square spaces and the lengths are 2.25. So these are the spaces and they're 2.25 each, right? And there's 64 of them. So remember, the area of a square is, base times height. So we got 2.25 times 2.25. So basically 2.25 squared. But we have 64 spaces. So we're going to multiply by 64. Okay? And that will give you the area of the regulation chessboard. And if we do that, we get 324 for the area. Okay, so that's the area of the big one. Now, remember what I told you earlier is that the ratio of the areas, or surface areas, in this case we're just looking at areas, the ratio of the areas is equal to the scale factor squared, right? So is equal to the ratio of the lengths, or the bases or whatever, squared. So in this case, they give us that number. This is the scale factor. Okay, just like we did here. This was a scale factor. And so was this. That's a scale factor. All of those are scale factors, meaning they tell you the relationship, between the dimensions, right? So in this case, A over B, they give you that scale factor is 4 over 225. So then we got to square that. Okay, so that means that A1 over A2 is equal to, we have to square this. 4 times 4 is 16, and then 225 times 225. Let's just figure out what this is on the calculator. So I'm going to do 4 over 225 times 4 over 225, and that gives me hold on. Yeah, so let's do this on the calculator real quick. So let me just do it over here. So we got 4 over 225 times 4, put that in parentheses, times 4 over 225 equals, okay, so 0.0003. All right, so 0.0003. And then we want to solve for the area of each square space on the world's smallest handmade chessboard. Okay, so we need to solve for A1. So what I'm going to do is I'm going to multiply both sides by A2 to cancel. So A1 is equal to that times A2. But we already know what A2 is. A2 is 324, right? So I'm going to do this times 324. And that gives me 0.1024. That's area 1. And remember that the area of the square spaces, there's 64 of them, right? Yeah, so there's 64 of them. So we're going to do this divided by 64. So the area of the square space is equal to this divided by 64. And that gives me 0.0016 inches squared. All right, so that takes care of number 2. 2 is A. All right, so number 3. 2 similar right pyramids have heights of 6 and 18 centimeters. The square base of the larger pyramid has a side length of 12 centimeters. So yeah, side length of 12 centimeters. Which of the following statements are correct? Select all that apply. All right, so first off, let's remember that what I said earlier was that the ratio of the volumes is equal to the scale factor to the third power. Okay, if it's the ratio of areas, is the scale factor to the second power. If it's the ratio of the volumes, is the scale factor cubed. Okay, so we know that in this case, we're looking at A and B are the heights, right? So I'm just going to go ahead and call this height. So height 1 over height 2. A over B can be any quantity as long as it's the same dimension, side length or whatever. In this case, heights. So in this case, the heights are 6 and 18 to the third power. And so if you did that, well, let's reduce the 6 over 18 to 1/3, because divide by 6 top and bottom. And then 1 to the third power is 1. 3 to the third power is 27. 3 times 3 times 3. Okay? So in this case, we get that the volume 1, and what we're going to do, so let me go ahead and say V1 over V2 is equal to 1 over 27. And we're going to solve for V2 here. So I'm going to multiply both sides by, or we're going to solve for V1. So we're going to multiply both sides by V2 so that these cancel. Okay, so then that means V1 equals 1/27th V2. So that means V1 is smaller than V2 by a factor of 1/27th. Okay, so I could just take V2 divided by 27 and I get V1. So that actually answers this question, is that the volume of the smaller pyramid is 1/27th the volume of the larger pyramid. So that answers that one. We want to select all that apply, so there's multiple answers here. The volume of the small pyramid is not 1/3, so this is incorrect. The volume of the larger pyramid is 864. We need to figure out what that is. So let's figure out the volume of the large pyramid. Remember that the volume of a pyramid is 1/3 base area times height. Okay, so since we have a pyramid that is square, a square pyramid, this is my capital B, which is base times height. Okay, this is the base, this is the height. And then this is the capital height of the pyramid. So I just basically have to do 1/3 little base, little height times big height in this example, okay? All right, so in this case, the volume of the bigger pyramid is 1/3 little base, little height, but the little base and little height are both 12. This is the side length is 12, so these are both 12. So it's 12 times 12 times, and then the capital height is 18 for the bigger one. Okay, so you're just going to do the math there, and you get 864 cubic centimeters. And the volume of the larger pyramid is 864, so that's good. All right, so let's take a look at part C. The base of the smaller pyramid is 3. Let's figure that out. How do I do that? Well, let's say this is the bigger one, and this is the smaller one, right? So let's call this base 2, and let's call this base 1. A little base 2, little base 1. So I just have to figure out the ratio of those two. That's all I gotta do. And the height, this is 12, right? Let's call this height 2, and this will be height 1. And this height was, what was that height? It was 6. Okay, good. So what we can do is we can say the ratio of the heights is equal to the ratio of the bases, right? So because it's similar, these ratios should be the same. If I divide the heights, that ratio should be the same as if I divide the same sides on the side lengths. All right, so h1 over h2. So 6 over 12 is equal to base 1 over base 2, which is 12. And I'm going to cross multiply here. So I get 12 B1 equals 72. Divide by 12 on both sides. B1 is 6. So it's going to be 6 centimeters here for both this and this, not 3. So this is incorrect. The volume of the smaller pyramid is 32. Okay, how do we know that? Well, the volume of the smaller pyramid is V1. V1 is 1/27th V2, but we already know what V2 is. So let's plug that in. So 864 divided by 27 is 32. So this does check out. All right, and that takes care of number 3. There's a lot going on in that problem. There's a lot of ratios and things like that that you gotta be careful with. All right, so 4.4, solve mathematical real-world problems involving the area of 2D figures. So we got ourselves an area of a hexagon. The best way to handle this, in my opinion, is to break it up into these shapes here, like that. Break it up into a triangle, 2 triangles, and then a rectangle. Okay. And then we just add them all up to get the hexagon. Remember that this is the height of the rectangle because it forms a right angle with the base. And this base here is how long? These are going by twos, by the way, so be careful. 2, 4, 6, 8, 10, 12. So this base here, that's 12. And this height here is 2, 4, it's 4. So we got 4, 12, 4, 12. And this is 2, 4, 6. This is 6. Okay, so area 1 is the same thing as area 2, right? Because they're both the same triangle. Area of a triangle is 1/2 base times height. 1/2 times 12 times 4. Half of 12 is 6. 6 times 4 is 24. The area of the rectangle, which is area 3, is base times height. 6 times 12. 6 times 12 is 72. So we have 72. We add these together. So we got area 1 plus area 2 plus area 3. We got 24 plus 24 plus 72. So that's 48 plus 72, which is a total of 120. And that's the best way to get the area of that. Just split it into those shapes. All right, so number 2, we have an earring, has the shape of a composite figure as shown. So we have basically this triangle and then this trapezoid, right? So we're going to do the trapezoid is number 1, and then the triangle is number 2. So, all right, so the area of a trapezoid is 1/2 times the height times a plus, or times base 1 plus base 2. Okay, this is base 1, and this is base 2 from here to here. And then we know that this is the height, right, of the trapezoid. And to get that height, I would have to do 3.5 minus 1, because this is 1 over here, right? So then this is going to be 2.5. The whole thing is 3.5 for the earring, the height, but then the height of the triangle part is 1, so this has got to be 2.5. All right, so that's the area of a trapezoid. Let's put it here. Area 1 is 1/2 times height times base 1 plus base 2. Base 2 is 3. So we got 1 plus 3. So in that case, the area of the trap is going to be 1.5. Oh, not the trap. I'm sorry. The yeah, that is supposed to be for the trapezoid. The trapezoid is going to be 5. Sorry. So yeah, 5, and then we'll do the area of the triangle next, which is 1/2 base times height. 1/2 times the base is 3, and then the height is 1, and that's going to be 1.5. I'm going to add those together, and that will give me the total area, which is 6.5. All right. That's number 2. Number 3, what is the area of the circle? All right, so the area of a circle is pi r squared. Now we need to get the radius. The radius is the distance from here, from the center to any point on the circle. But here they give us these 2 points, so we're going to use them, okay? So notice that we can use the distance formula here, right? The distance formula is square root x2 minus x1 squared plus y2 minus y1 squared. And that will give us our radius. So I'm going to call this r instead of d for the radius. Okay, so in this case, x1, x2, y1, y2. All right, so x1 is 3, so it's square root. Okay, it doesn't really matter the order if you do x1, x2, but we'll just do it in the order here. So x2 minus x1, 7 minus 3 squared, plus, and then y2 minus y1, 0 minus 4 squared. Again, like I said, the order doesn't matter here because you're going to square the number anyways. So even if you get a negative, it'll turn positive. So 7 minus 3 is 4. So 4 squared plus negative 4 squared. All right, so in this case, you get 16 plus 16, which is 32. Just do that on the calculator. Okay, so that's my radius is the square root of 32. We're not going to simplify that. We're just going to leave it like that because we're going to plug this into the area. So the area is pi times the square root of 32 squared. So the square root of 32 squared is just 32 because the square and the square root cancel. So that leaves you with 32 pi. There you go. That makes it a little easier. All right, a town has 23 city blocks, each of which has dimensions 1/4 mile by 1/4 mile, and there are 4,500 people in the town. What is the population density of the town? So first off, the density, the formula for density, this is the lesson that we haven't got yet done, just because of the sake of time. But to do the density, you just take the if you want to do the population density. If you think about it, the population density of a town or a city or a place is equal to the amount of people that is in that place divided by the area of that, the land area, right? And so if an area like New York City is very congested, then the population density is large, right? Because there's a lot of people per square mile. And in such a small area, there's a lot of people. So you take the population divided by the area, and that's how you get the population density. All right, so we need to figure out the area of the town. So the area of the town, well, there's 23 blocks, right? And each of them are 1/4 mile by 1/4 mile, so they're 0.25 miles. 1/4 mile is 1/4 of a mile, which is 0.25. So 0.25, 0.25. Each of those blocks is that. So this is for one block. And so the area of this is just 0.25 times 0.25. So it's 0.25 squared. And there's 23 of them, so I'm going to multiply by 23. So then the area is 1.437 square miles, 375 square miles. So that's the area of the town that they live in. And so in this case, the population density is equal to the population of the town, 4,500 people, divided by the land area. All right, so we got 4,500. Let's see here. Divided by 1.4375. And you get 3,130.4 people per square mile. Okay, for every square mile, you have that many people. And that's how you get the density, the population density. Number 5 is also a population density question. So we can go ahead and do that. So we're comparing two cities, Siesta Key and Destin, Florida. So we want to see which one has a smaller population density. So we're going to use D for density. So D1 is going to be the density of Siesta. And then we'll say number 2 is for Destin. Okay, so D1, the density 1, is equal to the population of Siesta Key over the area. Oops, I reversed it, sorry. The population was 5,573. The area for Siesta Key is 3.475 square miles. So if we do that, we get 1,603.7. And then for Destin, the population is 13,702 over the area 8.46. So Destin has more people, but it also has a larger area, so it makes sense that it has more people. So we're going to compare to see which one's bigger. Do this on the calculator, 1,619.6. So they're actually pretty similar in terms of population density, with Destin being slightly larger in density. So it looks like Siesta Key has a smaller population density. All right, number 27, page 27. All right, so it says solve mathematical real-world problems involving the volume of 3D figures. So number one, figure one shows the shape of a piece Julia is welding together for a sculpture. What is the volume of the figure? Okay, so we'll call this, we'll call this number one, call this number two, and then this number three. So because we have three different shapes here. So we have a hemisphere. So again, the volume of a sphere is 4/3 pi r cubed. The volume of a hemisphere is half that, right? So hemisphere is just half of a sphere. So instead of it being 4/3, it's going to be 2/3, right? Because half of 4/3 is 2/3. So we got 2/3 pi r cubed. The volume of a cylinder is pi r squared h. And the volume of a cone is 1/3 pi r squared h. Okay, and those are the three shapes that we have. We have these three shapes. So volume one is a hemisphere. So so 2/3 times. Now the radius of the hemisphere is 2, guys, because we got 4 divided by 2. It's half of the diameter. So it's 2/3 pi times 2 cubed. All right. So that 2/3 is 8. 8 times 2 is 16. So this is 16/3 pi. Volume 2, we could do that on the calculator later. Volume 2 is the cylinder. The height is 12, right? That's the height of the cylinder. And then the radius of the cylinder is 2. So pi r squared h. So that's 4 times 12 is 48. So it's 48 pi. And then volume 3 is the cone. Now the height of the cone, remember the whole thing is 21. And this is 4, right? So we have to be careful because that's 4. This is 12. So that's 16, right? So this is 6. From here to here is 16. And so that means from there to there is 21 minus 16, which is 5. So the height is actually 5 for the cone. Sorry, not 4. This is not 4. This is 2, because that's the radius, right? So this is actually 2. So that's 2 and that's 12. So this is actually 14. My bad. And so that means it's 21 minus 14, which is 7. Okay, so the height is 7. Okay, so in this case, we got the volume of a cone is 1/3 pi r squared h. Pi times r squared times h, which is, we said, was 7. So that's 4. 2 times 2 is 4. 4 times 7 is 28. 28 times 1/3 is 28/3. We got 28/3 pi. So now we're going to add them. So the total is V1 plus V2 plus V3. So we're going to just add up all these on the calculator, and you're going to get 196.7. So the answer is B. 196.9 is the closest answer. All right, so number 2, the weight of helium in a balloon can be estimated by calculating the volume of a sphere with the same diameter as the balloon's width. Helium has a density of 1.165. What is the weight of helium in a balloon with a width of 10? Okay, so this is here, the width is 10 inches. So we got to convert this to feet because this units here are in feet. So we got to convert 10 inches to feet. That's the diameter, by the way. So the radius is half of the diameter, right? So it's 10 over 2 is 5 inches. But then we have to convert the inches to feet. So remember, so there's 12 inches in a foot. So 12 inches in 1 foot. So the inches cancels out. So basically just take the 5 divided by 12. So in that case, that's 0.417-ish feet. All right. So that's how many, that's the radius of the balloon. And the reason why we need that is because the volume of a balloon is 4/3. The volume of a sphere, which is a balloon is going to be a sphere, 4/3 pi r cubed. So we have 4/3 pi times the radius cubed. So we're going to do that on the calculator, see what we get. So if you do that, you get 0.3037 cubic feet. Now to get the weight of helium, you have to take the density which is 0.165 ounces per feet cubed, right? And multiply it by the volume. And so you notice that the feet cubes cancel, leaving you with ounces, which is a weight, right? So that's how I know that we need to do that. 0.165 times 0.3037. All right, and if you take in chemistry, then you probably know how to do dimensional analysis. If not, you should practice converting between units. So you get 0.05 ounces. All right, so that's the weight of the helium in the balloon. Very small. All right, number 3. A cylinder has a volume of 300 pi cubic centimeters and a base with a circumference of 10 pi. What is the height of the cylinder? So, okay, the volume of a cylinder is pi r squared h. The volume of, or the circumference of a circle, right? The circumference is 2 pi times r. Now, they said that the circumference was 10 pi, right? And we don't know what the radius is. So we're going to use this to find the radius, 2 pi times the radius. So let's solve for the radius here. Let's divide by 2 pi on both sides. So we get 10 pi divided by 2 pi is just 5 because the pi's cancel. So now the radius is 5. So then we can plug that into here. All right. So they said that the volume is 300 pi equals pi times r squared, which is r is 5 now, times the height. So we had 300 pi equals 5 times 5 is 25, so it's 25 pi h. We're going to solve for h, so divide by 25 pi. Again, pi's cancel. 300 divided by 25 will give us our result. So the height is going to be 12 centimeters. All right, number 4, the diameter of a basketball is approximately 9.5 inches and the diameter of a tennis ball is 2.5 inches. The volume of the basketball is how many times greater than the volume of the tennis ball? So remember what I mentioned earlier, that the ratio of the volumes is equal to the scale factor cubed, right? The A over B cubed, that stuff, right? So in this case, the dimensions are the diameter. So we can take the diameter 1 over diameter 2, cube it. Okay, so the volumes are always related by that relationship. In this case, the diameter 1 is the basketball, which is 9.5. We're going to say basketball is number 1 and tennis ball is number 2. So 9.5 over 2.5 cubed. And then if I want to solve for the volume of the basketball, which is V1, what I'm going to do is I'm going to multiply both sides by V2 so I can cancel it out. So V1 is equal to, actually, I don't really need that, right? Because we just want, so I'm not going to do that. I'll just leave it like that. Sorry, Bob. I'll just leave it like that. I'm just going to figure out what that number is. So that's going to be 54.875, which is about 55. So what that's saying is that V1 is 55 times bigger than V2. So if I look at this, number, and I'll go ahead and multiply it just to kind of show you. The V2s cancel, so V1 is 55 times V2. So it's saying that the volume of the basketball, V1, is 55 times greater than the volume of the tennis ball, which is V2. All right, so number 5, Jeff is mailing a jar of jam to his grandmother. He finds a rectangular box just tall enough for the jam. which is the volume of the box that is not occupied by the jar. So we want to figure out what this space is here, the leftover space. All right, so in order to do that, I need to get the volume of the box minus the volume of the cylinder, and that gives me the rest, right? So the volume of the box minus the volume of the cylinder. Well, the volume of a rectangular prism is you just multiply the dimensions, right? It's base times height times base times length times height. So it's capital B times capital H, where capital B is little b, little h, and then you have the capital height of the prism. So basically 15 times 10 times the height, right? We don't know what the height is. 15 times 10 times the capital height. So 15 times 10 times the capital height. That's the volume of the box, minus the volume of the cylinder. Remember, the volume of a cylinder is pi r squared h. So the radius is 5, so it's minus pi times 5 squared times h. All right, so we got 150h minus 5 times 5 is 25, 25 pi h. And then if we want, we can factor out the h, and we get this. So basically I pulled out the h, and now when we use the distributor property, we get back to the original. The reason why I do that is because that's the answer, part C. So if I were to distribute this, that would be the answer that we got here, 150h minus 25 pi h. Okay, and that's my answer. Number 5 is C. Number 6, Alex is shopping for cheese, but she notices that the cheddar and brie have the same volume, even though their shapes are different. Based on the diagrams, what is the width of the brie? All right, so we know that the volumes are the same. Let's call this VC for V cheddar, VB for the volume of the brie. The volume of this is 10 times 3 times 4. So the volume of the cheddar is 10 times 3 times 4. So that's 120. And that should be the volume of the brie, right? So the brie, so be careful with this. To find the volume of the brie, this is a triangular prism, whereas this is a rectangular prism. So they're different. So this is the base area. So the area of a triangle is 1/2 base times height, and then I can multiply by the 10. So I got to get the area of the triangle first. So 1/2 base times height. The height in this case is W. Okay, so 1/2 times base times height, and then times this capital height. This is the capital height, and this is the lowercase height. So do the area of the triangle basically by multiplying these two, cut it in half, and then multiply by the depth or the height of the prism. All right, and then you get 15W. That's 3 times 10 is 30. 30 divided by 2 is 15. It's 15W. And then these volumes should be equal, right? So we're going to set them equal. So there you go, divide by 15. So W is equal to 8. All right, last one on the page. So a grain silo consists of, it's kind of hard to read that. Grain silo consists of a cylinder and a hemisphere. The diameter of the cylinder and hemisphere is 20 feet. The cylinder is 150 feet tall. What is the volume? Okay, so basically they give us the dimensions here, so we can just use that. So the diameter is 20, which means that the radius is 10 feet, okay? And then this is the capital height, and we know that the radius is 10 feet. So let's do that. We have two shapes, 1 and 2. Remember, the volume of a hemisphere is 2/3 pi r cubed. So 2/3 pi times r cubed. Volume 2 is, volume of the cylinder is pi r squared h. So pi times r squared times h. H is 150. All right, so let's go ahead and tell you what those numbers are. All right, so 10 to the third power is 1,000. 1,000 times 2 is 2,000. So this is 2,000 over 3 times pi. 10 times 10 is 100. 100 times 150 is 15,000. We have 15,000 pi. Then we add these together, and that gives me the volume of the silo. All right. In this case, we're going to add these. So we got to do 15,000 plus 2,000 over 3, and then multiply all that by pi. I'm putting the pi on the outside just so we don't have to deal with it until later. So we need to combine these two, the fraction and the whole number. The reason why is because in the multiple choice, it's on fractions. So that's why you got to practice your fractions. So in this case, the least common denominator is 3. So we're going to multiply this by 3. Whatever we do on the bottom, we have to do on the top. So we get 3 times that is 45,000. 1 times 3 is 3. Now we can go ahead and add these two fractions together. 45,000 plus 2,000 is 47,000 over 3 times pi. All right, 47,000 pi over 3. All right, so let's look at the next page here. All right, so GR 4.6, solve mathematical real-world problems involving surface area. All right, so instead of volume, we're looking at surface area. So let's go over some of the formulas for surface area. Here we got a cone and a cylinder. So the surface area of a cylinder or of a cone is, okay, so for a cone normally, here I'll just do it over here. The surface area is pi r squared because you have the circle on the bottom plus pi r L because you have the part that wraps around, right, on the top of the cone. That's the pi r L part. For a cylinder, you have the circle on top and the bottom, right? So that's going to be pi r squared plus pi r squared, which is 2 pi r squared. And then you have the part that wraps around, right? So like the wrapping paper in a can of baked beans, for instance, that wrapping paper wraps around that middle portion. And that middle portion is given by 2 pi r times h, where h is the height. So those are the formulas for surface areas for cones and cylinders. However, we want to keep in mind that for this particular object, right, we want the surface area of the container itself, and we don't care about the bottom of part of the container. We only care about the outer portion, right? So, and we don't even care about the bottom of the cone either, because they're all kind of meshed together into one object. So we are not going to do the pi r squared for the bottom. So we're not going to do that. And we're not going to do the bottom here because we don't care about doing that. We only care about the outer portion. Okay? And so therefore, we're gonna ignore this part and this part of the equation. We're just gonna focus on the pi r L and then the 2 pi r h. Okay, so the total surface area is gonna be pi r L plus 2 pi r h. All right, so we're gonna use that formula. This is the cone part, this is the cylinder part. All right, so this is L for the cone. That's the slant height. That's just here. Now, they do not give you the height of the cone, or actually, we don't need the height of the cone, actually. They do give us the radius. So the radius is going to be half of 24, which is 12. All right, so we got pi times 12 times 13 plus 2 times pi times radius, 12 times height, which is 10. So we get, so let's just plug this into the calculator and see what we get. We just plugged all that in. We get 1,244 feet squared. All right, so the answer is going to be C. All right, so number 2, the science team is creating a float for the homecoming parade. They want to make a rocket ship by using foam to create a cone that is stacked on top of a cylinder. The bases of the cylinder and cone will be congruent and have a radius of 1.5 feet. The height of the cylinder will be 4. The height of the cone will be 2. All right, so let's draw this out. So we have this cone part and then this cylindrical part. And so this is going to be 2. This is going to be 1. Shape 1. And they said that the height of the cylinder is 4 feet. And the radius is 1.5 feet. So we'll just say that distance there. All right. All right. So, and then if all the visible surfaces need to be repainted except for the bottom. So we're going to ignore the bottom when we do the surface area. So again, so let's write that formula out. So the surface area of the cone is normally going to be, I'll write it off to the side, pi r squared for the bottom plus pi r L. But we're going to ignore the bottom because that is meshed to the cylinder itself, right? So it's just going to be pi r L. Surface area 2 is, so normally the surface area of a cylinder is 2 pi r squared plus 2 pi RH. However, we're not painting the bottom, and we're certainly not painting the top because that is meshed to the cone. So we're going to ignore this part of the equation, and we're just going to do the 2 pi RH. All right, so in this case, we have pi times radius times L. We need to figure out what L is. We don't know what L is. Actually, do they tell us? Let's see here. This is the cone will be congruent, have radius here. Okay, so they tell us that the height of the cone is 2 feet. That's 2 feet. However, they do not tell us L, and we need to know what L is. But notice that this makes a right triangle. So what I'm going to do is I'm going to use Pythagorean theorem to get that L. Okay, so here's the triangle. The right triangle is 2, 1.5, and L. So a squared plus b squared equals c squared. All right, so we're going to do 2 squared plus 1.5 squared equals L squared. Then we got to take the square root to get L. So L is equal to all of that. So if I do that on the calculator, let's see what we get for the L, shall we? We get 2.5 approximately. All right, so that's my L. We're going to plug that into L here, this guy. So we get pi times the radius, which is 1.5, times L, which is 2.5. And then here we got 2 pi times radius times height. The height was 4. We're going to add these together, and that'll give us a total surface area. We're just going to add those together in the calculator. You get 49.5 feet squared. All right, so that's number 2. Let's do number 3. The surface area of a right cone is 364 square inches. If the slant height is 6.5, what is the radius of the cone? Okay, so this time we're going to do the whole thing. We need the surface area of the cone, which is pi r squared plus pi rl. So this time we're doing the whole thing. There's no restrictions on what we're going to do. So they said that the surface area is 364 equals pi, and then the radius is, we don't know the radius. We were trying to find that. And then the radius, we don't know here. The L is 6.5. Okay, so basically what I'm going to do is I'm just going to put I'm just going to change this to 6.5 pi times r. And I'm just going to put the 6.5 in the beginning just to make it look nicer. So now what we're going to do is I'm going to get rid of the pi's. So I'm going to divide both sides by pi. That way these cancel. And that way I don't have those pi's messing around. So 364 divided by pi, let's do that on the calculator. That's about 115.9. And then we got r squared plus 6.5r. All right, so now that looks cleaner. Now notice that this is a quadratic equation. You can only solve quadratic equations by factoring, there's a lot of methods, but you can also use by using the quadratic formula. We haven't really done much with the quadratic formula in this in this year. However, there's a possibility that you may have to do something like this. So we want to make sure that we cover it just in case. So what you want is, if you have a quadratic equation, meaning you have a, like a squared, you need to make one side equal to 0. So you're going to subtract the 115.9 on both sides. And that'll make that one side 0. Okay, now that one side is equal to 0, you can use the quadratic formula here. So the quadratic formula, remember, is x is equal to, in this case, x is r, so I'm just going to use r. Negative b plus or minus the square root of b squared minus 4 times a times c all divided by 2 times a. If you guys remember that, that's from Algebra 1, the quadratic formula. You just plug it in and then you get the answer. So remember, a, b, and c. A is that, which is an invisible 1. That's b. And that's c, which is negative 115.9. So we got to plug those into that equation, into the quadratic formula. So again, this is called the quadratic formula. All right, so negative b, which is 6.5, plus or minus the square root of 6.5 squared minus 4 times a is 1 times c is this negative number, all divided by 2 times a, and a is 1. All right, so we're going to do that on the calculator. And when we do that on the calculator, we're going to get 2 answers there. Okay, so we're going to get 2 answers because we have to do the plus version and then the minus version. So we got to do negative 6.5 plus the square root divided by 2, and then negative 6.5 minus the square root divided by 2. So we get 2 answers here. So negative 51.48, and then the other answer is 8. Now, obviously, 8 is going to be the answer we want to use because we don't want the radius to be negative, right? That doesn't make any sense. So we're not going to use that answer. So that means the radius is 8. So we're going to say it's 8 inches for the radius. Okay, so that was a pretty advanced problem as far as doing that because that involved the quadratic formula. Number 4. Kristen and Rachel are hosting an art show where they'll showcase the local artists' sculptures. They're painting pedestals upon which the sculptures will be placed. Pictures of the pedestals will be shown. They'll be using are below. 1 gallon of paint can cover 400 square feet. How many gallons of paint will they need to purchase to cover at least 4 of each type of pedestal? Assume that the base of each will not be painted. Okay. All right, so we have to figure out how many gallons of paint will they need to purchase to cover at least 4 of each type. So there's 4 of each of these guys, and we want to figure out essentially what they're asking for is the surface area. The surface area is, that where we're going to paint over. All right, so first off, let's go over the formulas for calculating these. So for the rectangular prism, which is number 1, I'll call this number 1, 2, and then 3. So for number 1, the rectangular prism, the surface area formula is given by, so basically what we need to do is we would need to add all the surfaces except for the base, right? Except for the base. And when they mean the base, they're referring to like this bottom part, right? So that's the base that we're not going to do. So we're not going to touch those. However, they are going to cover the top base here. So we have this area, this area, this area, the back, and then the left. Okay, so to get the area on the top, this area on the top, we have to multiply the base times height, 2.5 times 2.5. Okay, so let me actually do that over here. So surface area 1, so we have the 2.5 times 2.5, which is 2.5 squared. So that's this top part. And next we want to do this part here, which is 2.5 times 3, because that's 3, right? So plus 2.5 times 3. And we have 4 of them, right? 1, 2, 3, and 4. We have 4 of them and they're identical. And so we're going to multiply this by 4 just because we have 4 of those surfaces. That's going to be our surface area. We're not going to do the bottom part because like they said, the base is not going to be painted. The bottom part, we're not going to paint it. All right, so we got 2.5. So if we do this math, we get 36.25. And then we're going to do the surface area for the cylinder now. Now the surface area for a cylinder, is normally 2 pi r squared plus 2 pi rh, right? That's normally the formula. However, the 2 pi r squared comes from the two circles. We only want to do one of them, right? So we're gonna basically just turn this into a 1. Okay, so we're only gonna do 1 pi r squared. Okay, so pi r squared plus 2 pi rh. So pi times the radius. Now the radius is half of 2.5, which is 1.25. We got to do half of that. Plus 2 times pi times 1.25 times h, and h is, the height is 3 here. We add that together, we get 28.47. And then we need the surface area for the, this is a trapezoid, or this is a triangular prism. All right, so remember we're not going to do the bottom part, but however, the top part, this part right here, is a triangle, and it's an equilateral triangle. Okay, so all of those sides are 2, so they're equilateral. So there's something that we need to discuss about that because we need to get the height of that equilateral triangle. So I'm going to show you how to do that. So because it's equilateral, that means each of these angles are 60, right? Now, because each of these angles are 60, if I were to cut this in half to get the height, to make a right triangle, and this triangle right here is going to be a 30, 60, 90 triangle, and I'm gonna blow it up and make it bigger because we need more room. Okay, so this is the height. This is 60 degrees, and now since this is getting cut in half, this is actually going to be 30 because it's cutting the 60 in half. And then we know that this is 2, and then this is getting cut in half, so this is 1, right? So remember, in a 30, 60, 90 triangle, you have x square root of 3. I think I call it a, right? So I call it a square root of 3, and then 2a. Well, in this case, a is 1. You can see that. And so h is going to be 1 times square root of 3. So we can easily compare that. So h is equal to square root of 3. All right. So now that we know the h, we can do the base times height. So the area of a triangle is 1/2 base times height. Remember, area of a triangle equals 1/2 base times height. The base here is 2. All right, so 1/2 base times height plus, now we got to do the surface area for, so now let's look at this part. The area of that is 2 times 3, right? So 2 times 3. And we have 3 of them. We have this one here, we have this one off to the side, and then the other one off to the side. So we have 3 of them, so I'm going to multiply them by 3. All right, so in that case, I get 19.73. And next, I'm going to add these surface areas together. So if I add those, I get 84.45. And next, I'm going to multiply that by 4 because we have 4 duplicates. Right, so we have 4 copies. So these are the duplicates. So we're going to times that by 4, and we get 337.8 square feet. And then finally, we're going to take that and divide it by the square foot per gallon. So we're going to take that number, divided by the 400, and that gives us 0.8445 gallons. So we're going to need less than a gallon. We'll be able to cover them with less than a gallon, assuming that the gallon can cover 400 square feet. All right. So next page here, these are covering 2 standards, copy constructions for segments and bisectors. All right, so number 1, what is the final step in this construction? Very straightforward. This is actually how you construct the perpendicular bisector. So normally what you would do is to construct the perpendicular bisector, here are the steps. You basically put your compass and you set the width of the compass so it's greater than half of the line. So this is greater than half. And then you're going to, and this is the pencil end, okay? So this end is the pencil end. And then you're going to trace an arc above and below. Well, we'll have to do one above here and one below here. And then without changing the width of the compass, you're going to put the compass at point H, and then this is the pencil end. Then you'll draw this arc and this arc, right? And then once you draw those arcs with the compass, and you can draw them as circles if you want, but arcs are just, easier to erase. And then once you do that, then the final step is to basically use a straight edge to connect those two. And that will be your perpendicular bisector. Okay, so that's basically the basic steps. So we're going to use a straight edge to connect points A and B to G and H. Actually, not to G and H. Sorry. Use a straight edge to connect points A and B. That's it. All right, and that's it. So number 2, in order to construct the interior point of angle CAB for the angle bisector, where should you place the compass point? So I'm going to run through the steps of how to do it, and then we'll answer the question, just to remind you. So first off, we have this angle. So in order to do the bisector, you would have to essentially, so you would have to place a compass here, point, and then let's say this is the pencil end. And then you're going to draw an arc there. And then you're going to, keeping the same setting, you're going to put the compass point here. And then let's say that this is the pencil end now, right here. And then you're going to draw an arc there, right, with the compass. Once you do that, then you'll have the arcs that should cross. And then you're going to connect those. And this will be your angle bisector that's going to cut this angle in half. Okay, so like I said, in order to construct this interior point, you would have to put the compass on B and C. So the answer is D. All right, number 3, select all the statements that describe the steps to copy X, Y. So the steps to copy X, Y, we can just answer them here. So you're going to take a straight edge and you're going to draw a line. Okay, so using your straight edge. So we'll draw a line and we'll call it line L. And then we'll label one of the points M. Then what you're going to do is you're going to use the compass in order to measure the distance between X and Y. And then you're going to take that compass and place it on your line that you made, and you're going to make an arc. And that will mark where the line should terminate. So that way the length has to be from M to that new point. And that's how you do it. So use a straight edge to draw line L at point, and then label one of the points, whatever you want to call it, in this case M. Place a compass point at X and open the compass to length XY. That's what we were saying here, like keep that width. Using the same setting, place the compass at point M. Yep, the same setting there. Draw an arc through line L and mark point N as an intersection. There you go. With a setting greater than 1/2 XY, place a compass point at X. No, that's not correct. And it doesn't have to be a ruler. It can be any straight edge. All right, number 4, below the steps of copying DE using dynamic geometry software, which sequence has the steps in correct order? All right, so first off, we have to basically draw, let's see here. So we're going to draw a point. So let's say, and then label it something. In this case, label it G, whatever. And then what we're going to do is, so let's say that this is DE. Then once we do point G, then we're going to measure this with the, normally you would measure this. Basically what you do is you make it so that you make it so that this is the radius, right? And so you would, let me put the point G over here, so that radius is the same distance, and then you're going to draw a circle using the software. All right, this is what you would do, like for example, iExcel or something like that. So you would draw a circle with the radius, which is equal to this length, and then you're gonna draw this other. You're gonna put a point here, and that will be your line segment, right, on the point on that circle. So first off, you're gonna draw a point and label it whatever you want to call it. You're gonna construct a circle with the same radius as this, right? So you'd have to measure that radius and then draw the circle. And then you're gonna draw that circle, and then you're gonna put the end point on that circle. And then in that case, it would be congruent. Then we can erase everything else and then say, okay, well, then they're now congruent. So it's going to be 4, 2, 1, and 3 is the order. All right, so number 5, below are the steps for constructing the perpendicular bisector of MN, which sequence has the steps in correct order. Now, we kind of talked about the steps here, so we can kind of go through it relatively quickly compared, because we kind of did it over here when we did number 1. So first off, you're going to want, so we know that this is MN, so that's going to be a given that we draw it. All right, and then we're going to do the compass so that it's a little bit more than halfway. That looks like step 5. Place the compass so it's longer than half of it. So step 1 and 5. So it looks like one of these. And then you're going to draw an arc above and below, and then repeat that for the other side. And then once you do that, then you're going to okay, so that looks like step 4. Without adjusting the compass, place at a point N. And then lastly, we're going to label the intersection of these points and then draw a line through them. Okay, so in that case, that looks like answer not B, because it looks like D. All right. All right, guys, so we're a little bit over an hour into the video, so we're going to go ahead and cut it here, and we'll finish it in another part. All right, thank you guys for watching this video. I hope you learned something. I'll see you in the next one.